Can I, can I start now?
Yes, please do.
Okay, I have that already gave the introduction. Okay, so for people working in quantum gravity, the Euclidean path integral is a very powerful tool, right? We can compute the partition function and can extract, for example, thermal properties, and you can also use the partition function to constrain possible microscopic models. But the the Euclidean partition function is not always positive definite because there are negative modes. And in this case, the statistical interpretation is not clear. So it's important to understand the phase of the nature of the phase of the potential function. And here I list a bunch of interesting papers discussing the phase of the Euclidean. For example, the first paper is by Gibbons, Hawking, and Perry in 1978. They studied the Euclidean partition function when the cosmological constant is zero, and they didn't find the phase, but they speculated that in other Einstein manifolds there might be a phase due to negative modes. And just 1 year later, Hawking confirmed that the Euclidean passing integral on sphere, basically it's on sphere because it has he can see the positive cosmological constant. He found some phase, but he didn't get the full all the negative modes. And 4 years later, Ginsburg and Perry compute the phase on S2 times S2, which is also a Einstein manifold in 4 dimension when the cosmological constant is positive. And they find the partition function to be proportional to I, which is in favor of their proposal about the instability of the theta, which means that the theta can tunnel to S2 times S2. But we are sure that their calculation is not correct because they didn't treat the conformal part or the y part of the metric fluctuation correctly. And to me the first careful treatment of the conformal part is due to Pochinski, and he found that the Euclidean partition function on d-dimensional sphere has a d plus 2 factors of I, and because of this Coleman's argument of why lambda should be very small does not work in general dimensions. And more recently, the phase attracts more tensions. For example, 5 years ago, with Diehl, Frederick, and Albert, we compute the phase for high spin gravity on sphere. And last year, maybe just five months ago, Juan Marceno wrote a paper. He tried to include an observer into Pochinski's calculation to get rid of the phase and to get a Kantian interpretation of the entropy or the partition function. But in the end, an overall minus sign still remains. And just this week, Diehl and his friend wrote a paper about the partition function for CP2, which is the subleading saddle point between S4 and S2 times S2 in 4 dimensions, and they found that a factor of I or minus I because there's a single negative mode, and inspired by all these works, we together with Victor and Juan, we revisited Pochinski's calculation, and we tried to clarify some additional subtleties that's overlooked in that paper. And as a natural follow-up, we compute the phase for more general Einstein manifold that takes form of the SP times some compact manifold MQ. And that's the plan of the talk. First, I'll review Pochinski's calculation and explain what's missed there, and then I'll explain how we compute the Euclidean passive integral on SP times SQ, and we'll give a Lorentz interpretation for the phase we got there, and I have some more extra comments for in the S2 case, S2 times SQ case. and I have some then some overlook and
Zimo, before you go, can I just ask you a question about this phase? Is it understood that, or is it believed that's a pathology that has to be getting rid of, or could it just be that's just how life is? For example, isn't it true, like
There,
in
there, there there are arguments like some people don't think the Euclidean path integral is the correct way because you don't have a negative definite, a positive definite action. But here we 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 think that we need to understand more. There might, for example, in Huang's paper, he tries to include the observer, and maybe in the observer plus the set of system it has a positive partition function.
But I guess my question, isn't it true that it's known that I think in digravitation theories, there are theories with partition functions are,
Mhm.
right? In other words, it's not a pathology, the theory, right?
Yeah, you can have even in ADS, right? You can have negative modes, and in those cases, you'll get negative. You get imaginary partition function. It's just it is. Yeah.
But just to clarify, it's not, I just want to make sure I understand the imaginary number of phase is not saying the theory is sick. It's just that we
Mhm.
wish to be counting
Yeah, yeah,
some.
yeah, yeah,
Our wish.
yeah.
Okay.
Hmm. Right.
Yeah. Great.
Okay. So now, so here this is the quadratic action for linearized gravity in capital D dimensions. So I will also use small d, which is a capital D minus one, and I choose the cosmological constant lambda to be d times d minus 1 over 2, and that's how I got this action. And it has a gauge invariance, the diffeomorphism as gauge invariant. And okay, the operator delta 2 is defined here with some Riemann tensor involved in the definition. And H is the chase part of the metric fluctuation, and a the the gauge fixing term used in Ploczynski paper is the Donda gauge, and here it's a convenient gauge because it cancels term in red in the original action. For example, the square of the first term cancel this the third term here, and the cross term after integration by part, it cancels the last term here. So in the end, what's left is the first two terms and this extra piece. And when you combine these two, the original action and the down the gauge, and then you decompose the metric fluctuation into a traceless part, which is denoted by h bar here, and the trace part, which is denoted by h, you get this decoupled action. So the h bar part is perfectly positive, definite, and but the trace part, or sometimes called the conformal part, it has a round sign Gaussian because of the extra minus sign in front of it. And if you look at here, Laplacian square, the Laplacian is defined on SD, and the spectrum is L times L plus small d, and L is the SO d plus 1 angular momentum. So you see that for almost all the modes, the action is positive definite for H. And how can we make sense of such a path integral? Okay, let's first consider a single round sign Gaussian integral. Okay, here we can the usual Gaussian integral is defined for in this case it defined for z that whose real part is positive, and then you get it's 1 over square root z. But for 1 over square root z, you can continue it to the almost the full complex plane except the branch cut here. And then you can define the round sign Gaussian by approaching the contour from the branch cut from above or below. And they give different faces. And it's either I or minus I. And our strategy is that we complexify the G Newton, which is in front of the action a little bit, such that the inverse of G Newton has a negative imaginary part. And because of this choice, this choice corresponds to the plus sign here, corresponds to the minus sign here, and has each negative mode contributes effect of minus I. But okay, at this point, we don't have a very good justification for this complexification. That's just say we choose this one and we proceed. We hope to solve this to give a better reason for that later. Okay, that's how we deal with a single round sign Gaussian. But the problem now is that we have an infinite number of such Gaussian integrals, and how can we sum up this phase? And that's what's missing in Pochinski's original papers, because naturally there are two ways to do that. The first prescription is that we can just weak rotate the contour of H to the imaginary axis, such that most of the negative modes become positive, and the new negative modes are what's positive before, and that's the L equals 0 and L equals 1 modes. And if you look at the equation, right, L equals 0, you get minus 2D here, and you have the minus sign is plus 2D. And similarly, for L equals 1, you get D minus 1 here. It's also positive, but for higher L, you get negative modes. So because of our prescription, the complexification of G Newton, I just told you, there'll be D plus 2 factors of minus I. This one comes from the constant mode, the L equals 0 mode, and the D plus 1 comes from the L equals 1 mode. And actually, the L equals 1 mode is missing in Hawking's original paper. He only noticed the constant mode. And
before you go on, I'm sorry, I think I just missed something important. So can you explain what was the point of the wick rotating the G Newton again? Can you say again?
Because we want to approach the branch cut, right? But it depends on how you approach it. This small I epsilon just tell you how you approach it from above or below.
Okay, I see. All right, thank you.
And there's in the second prescription, we don't do any wick rotation, so we get an infinite number of negative modes, and they gives minus I to infinity, almost infinity. But we have some positive modes, so we need to subtract the positive modes, which is D plus 2 of them. And here so I get this factor minus I to infinity, and by that I means it involves all the modes of a full scalar field, so it's ultra local, and it can be absorbed into a local curvature quantiterms. So I drop this type of divergence term, and what's left is I to D plus 2. So you see that compared to the first prescription, it's I instead of minus I. And then we can ask which is the correct prescription. And that's one thing we resolved in this paper. And it's very similar to a problem Pochinski considered about the ghost part of the path integral. Okay, if you want to use the Faddeev-Popov procedure for these kind of path integral, you have a absolute value for the ghost part, absolute value of a determinant. But if you just use the BIST procedure, you don't have a absolute value. So then what's the correct one? These are without the absolute value, and Pochinski noticed that the phase of the ghost determinant depends on the gauge fixing term. So in order to get a gauge invariant result, you have to it's more natural to choose the absolute value prescription. And we will use a similar idea here. So before we choose the Donder gauge, and now we choose a more general gauge. We put the two parameters alpha and eta here. So it defines a more general gauge, and we want to compute the phase in this gauge choice with this gauge choice. Okay, but it's not as convenient as before because the traceless part and the conformal part don't decouple in this gauge. So we'll use a different decomposition for the metric fluctuation. So we first psi mu nu is a transverse and the traceless part, and then we add this psi nu part, which is transverse vector. And for this decomposition to be unique, it should be orthogonal to Killing vectors, right? Because for Killing vectors, this d mu psi nu plus d nu psi mu vanishes. And then we also have this chi prime part. It corresponds to longitudinal psi basically. And okay, it's the L equals 0 and the L equals 1 mode should be excluded in psi prime because, for example, the L equals 0 mode is just a constant and it does not contribute here. And the L equals 1 define also vanishes because I subtract the trace. And in the end, you have the Weyl factor, the conformal factor. So that's a unique decomposition. And you can rewrite the action in terms of these components. And after a single field redefinition, you can decouple all the fields. And for the redefine the chi prime and the phi, the chi prime has some negative mode, is a mostly positive, and the phi is mostly negative because phi is the analog of the Weyl factor. But the problem here is that the number of negative modes depends on alpha and eta. So it depends on the gauge fixing term. So here I'm for chi prime, there's a minus d plus 2 because I exclude the L equals 0 and L equals 1 modes. Okay, let's see. If we follow the first prescription, we rotate phi because it's the Weyl part. And then the spectrum becomes mostly positive, and it's almost identical to the spectrum of chi prime, except that it includes all the modes. So then so each negative mode contributes a effect of minus I. So we have minus I to 2n minus d plus 2. And they see that the final result depends on what n alpha eta is. So it's not gauge invariant. It's not gauge invariant. Oh, it depends. And if we use the second prescription, right? For the chi prime part, it's the same as before. So that's the second. It's this factor here. And for the phi part, we have we use this it's infinity minus n alpha eta, and we can drop minus I infinity. And you see that minus n alpha eta and plus n alpha eta cancel, and what's left is just I to d plus 2. So it does not depend on the gauge fixing term. So in this sense, it's this should the second prescription should be the correct one. And because of this, and we will use this prescription in later. And just a quick summary, this prescription just tells us that every positive mode of the conformal factor contributes a factor of I, and all the other negative modes contributes minus I. Any questions here?
Zemo, just a quick just to orient my thinking. So it seems like you're trying to find the correct sign in front of I, but you're not getting rid of the I. So in this talk, the I is
Oh,
going to
I'm
be
not getting rid of that. That's exactly the I Pachinski find.
okay.
I'm not trying to get rid of I. Just look, you get two different results, and they give different phase. I'm just showing which one is the correct one, which phase is the correct.
I see, but just because I'm naive about this, I don't understand. So what is the physical implication of having a plus I or minus I? Like this, what kind of observables or
Yeah,
computation?
I'll discuss it later. Just here, just the technical part to explain what we did and what's the correct way to compute things.
Okay, all right.
Yeah, here the just we can forget about this technical part. The summary that every positive part in the conformal factor contributes I, and the other negative mode contributes minus I. And I see here some general comments. This decomposition works for any compact manifold, and and from the chi prime phi system, what you get is I to 1 plus n, the number of conformal Killing vectors that are not Killing vectors. So on sphere, it's just the L equals 1 mode, and if the manifold is not sphere, this NCQV is always 0. So you just get the factor of I. And on sphere, the psi mu nu, the TT part is positive, and we didn't care about it. But in general, the TT part can also have negative modes. And for example, on S2 times S2, there is a one negative mode, and on CP2 there's no negative mode. And the psi mu part is always positive because it's just a gauge transformation. It does not appear in the original action, and it only appears in the gauge fixing term. And the gauge fixing term is positive definite by construction, so it does not contribute any phase. So for a generic for a general manifold Einstein manifold M, this is the expression. This is the total phase. You have minus I to n tt and I to 1 plus n CQV. And we know that the CQV part is easy. I just explained, or it's 0 mostly. So we'll show how to compute this TT part. We give a efficient calculation method, and for the case of SP times SQ. Okay, and for some manifold, this TT part can also have 0 modes that's related to the moduli space of Einstein manifold. In this case, we need to go beyond the quadratic action. Let's not go into details here. Okay, and maybe people can ask if, okay, is this phase physical, or in other words, does it depend on the scheme, right? Because if it can be removed by some curvature conterms, it's not physical. Here, I want to argue that it is physical in the following sense. For example, in 4 dimensions, we have two types of marginal curvature conterms. Scheme here, right, in a very schematic form. So epsilon is the total antisymmetric tensor, and R is the Riemann tensor. So you can have you have this tau. Tau is because it involves only one total epsilon tensor, so it breaks its parity out. And since we started with a parity even theory, we don't want it to use a parity odd term to absorb the phase. And chi is parity even, but adding I in front of chi leads to a complex Hamiltonian, and we don't want that. So in this sense, we the phase is physical. So in maximum theory, I think the analog of tau is just f wedge f, and chi would be f wedge, the Hodge of F, something like that. Okay, so I just want to say that the phase is physical, it's not scheme dependent. Okay, now let's consider the path integral on a product Einstein manifold that contains a vector of sphere. And to be more explicit, I will only consider the product of several spheres here. Let's first start with the product of two spheres. So for two spheres, we can decompose the metric fluctuation as follows. So this phi is still the overall Weyl factor, and phi alpha beta is traceless on the first sphere. So alpha beta labels the index on the first sphere, and alpha prime beta prime are the indices on the second sphere. So sigma is the subtrace on each sphere, and since we define phi as the overall trace vector, the sigma, when you take the trace, the sigma part cancel out. That's a convenient decomposition of the metric. And now if we choose the down the gauge, all the modes here decouple. Okay, each alpha beta prime means the off-diagonal part of the metric. And they decouple, and they are positive definite except the phi and the sigma part. So phi is the Weyl part. It has a round sign Gaussian, and sigma, it's mostly positive, but the low-lying the low-lying modes are negative definite. For example, the constant mode, right? For the constant mode in sigma, the Laplacian square is 0, and what you get is minus 2D. So, but okay, according to our prescription, each negative mode in the Weyl part phi contributes a factor of I, and each positive mode in sigma contributes a factor of minus I. And you see, because they differ only by an overall minus sign, so the negative mode of sigma is paired with the positive mode of phi, and you get a product of, you have minus I and I, so it's always positive. And hence for the SP times SQ case, the total phase is 0. You get a positive result. And the calculation for more spheres is similar, right? You can do a similar decomposition, and you get the overall phi, and you have sigma I, the subtrace on each sphere, and it's subject to the constraint that sum of sigma I is 0. So you get n minus 1 independent sigma I. And okay, say that the action of sigma I and phi is the same as before. So let's see that you have m minus. So let's say the negative mode of this is m minus. So you get I to m minus from the Weyl part, and you have minus I to m minus times m minus 1 from the sigma I. And that's what you get. As minus I to n minus n minus 2 times n minus. And so that's the remaining question, is how to compute the total number of the negative mode, the n minus. And okay, the spectrum of the Laplacian on the product manifold is very easy, because from the Einstein manifold condition, we can get the radius of each sphere, I, and it depends on the dimension of the sphere, and we get this expression. And you see that if all the spheres, the dimension of all the spheres are larger than 2, each factor is bigger than 1. So when it's because you have a d overall d, then each factor the whole thing is for a fixed I, the whole thing is bigger than d, and you cannot have more than two L equals one mode or so. Okay, and this the negative modes are just the constant modes on all the sphere, or you can have one L equals one mode on one sphere, and that gives the n minus because the LX1 mode can be on on any sphere. So we get pi plus 1. That's the number of L equals 1 modes on the ith sphere and the sum of I. And the sum of pi gives the total dimension d. And so n minus is d plus n plus 1. Okay, but there is a question. There is a small loophole, and because when pi equals 2, the L equals 1 mode becomes a 0 mode, right? So here, if pi is 2, p minus 1 is just 1. And if Li is 1, you get 2 here, and you have d, so it's 2d minus 2d. You get a 0 mode. And you can ask if these 0 modes are removed by corresponding ghost 0 modes. Okay, let's go see the S2 times S2 case in the Dodona gauge. We found there are 12 bosonic 0 modes. They are the 0, 1, and 1, 0 modes in both phi and sigma. But we only find the 6 fermionic 0 modes. Seems that naively there is a mismatch of the 0 modes. And it is a contradiction. Let's see. We can see let's deform the Dodona gauge a little bit. We add this epsilon here. It's a very small number, and we found that the 12 bosonic 0 modes mix at order epsilon, and they are lifted to 6 positive modes and 6 negative modes. Or you can consider just that you have a 12-dimensional Gaussian integral with a vector of epsilon in front of it. And from this 6-dimensional Gaussian integral, you get epsilon to minus 6. And it's exactly cancelled by the ghost part, because the ghost part, you have 6 ghost modes, and it's also all the epsilon. So you get epsilon 6 to 6 from the ghost part. So in this sense, there's no contradiction. It's just an artifact of the gauge choice. Okay, here there are a bit more technical comments on this phenomenon. So we consider because I won't say that these strange unmatched is due to the non-positive definiteness of the action of gravity. So if we consider gauge theory with a positive Lagrangian, and we add the gauge fixing term f square, if we don't choose the gauge fixing term properly, there are some residual gauge symmetry, which means that there are some pure gauge field configuration phi, such that both the action and the gauge fixing term vanishes. Now let's modify the gauge fixing term. We can f plus epsilon g, and we evaluate the new gauge fixed action on phi, and we see that it starts at order epsilon square, because the cross term epsilon fg vanishes because f itself vanishes, only epsilon. So yeah. So if we have n bosonic 0 modes, we'll get epsilon to minus n, because it's epsilon square in front of the Gaussian integral, and it's cancelled by epsilon n to n from the same number of ghost 0 modes, because ghost from the BST, it's easy to see that the ghost action is always all the epsilon on the 0 modes when you evaluate on 0. And an example is the Stuckelberg action of a Proca field, and you choose the gauge fixing term to be d mu a mu. I'm not going into the details here. And the gravity is different because for gravity, the gauge fixed action is not positive. So in addition to the residue gauge symmetry, there can be some accidental zero modes such that the combined action, the gauge fixed is action is zero, but the original action and the gauge fix and the gauge fixing term are not zero. That's different from the residue gauge symmetry. So among the 12 bosonic zero modes we found in the S2 times S2 case, 6 of them are diffeomorphism, which means they are residue gauge symmetry, and the rest 6 are accidental. And we can always avoid these accidental zero modes by using a different gauge. And that's what for example, that's what this epsilon deformation means. Okay, here, anyhow, it just means that the zero mode is not this accidental zero mode is not a big problem. It does not affect the counting of zero modes. So even you have some so even in the S2 times S2 case, the overall phase is zero. It's the same as SP times SQ. So this formula works for PQ starting from 2. And similarly here. Any questions? Okay, no questions. Perfect. So the calculation I just showed can be summarized as follows. We can see that the Euclidean path integral on SP times SQ, and it has some factors of I. I write it in this way: I to P plus 2 times minus I to N. So I times P plus 2 is the same of the phase of pure gravity in the theta in p-dimensional the theta space, which is the weak rotation of SP, and N denotes the extra phase. And for example, if MQ is also a sphere, then this curly N is P plus 2 because we know there's no phase. And okay, what I'm going to do is that I'll explain that the extra phase N is due to some tectonic fields in the theta P arising from KK reduction on the internal manifold MQ. And more precisely, N counts the physical instabilities, which is also the number of some weighted sum of the growing quasi-normal modes in the static patch of the theta P.
Zemo, maybe I think I missed something. So you write SP times MQ there,
Mm-hmm.
but in the past few slides, weren't you always choosing MQ to be a sphere?
Yeah, I just show it explicitly when MQ is a bunch of spheres, but it works in the general case. In the
Then
paper we can see the more general case, but here I just showed some examples of MQ.
what do you mean by general case? MQ can be any manifold.
For any compact manifold, such that the product is a Einstein manifold.
Okay.
And then the phase depends on the details of the geometry of MQ. Okay. Okay, now next I explain what I mean by like growing quasi-normal mode or the physical instability. So let's start from a toy example. We can see a inverted simple harmonic oscillator whose Euclidean action is given by this. Because this minus mu square, it's inverted, and we choose it's defined on the circle of period 2 pi of length 2 pi. So the modes are just the Euclidean modes are e to I n tau, and when the absolute value of n is smaller than mu, it defines a negative mode. So the total number of negative modes is 2 times the integer part of mu plus 1. And on the other side, you can compute the unshared modes in the Lorentzian signature, and you get E2 plus minus mu t, and then the E2 mu plus mu t can be thought as a growing quasi-normal mode, and you see that so the number of Euclidean negative mode is related to the frequency of the growing quasi-normal modes, and more precisely, what we are trying to argue is that the number of Euclidean negative modes can be written as a sum of the growing quasi-normal modes, and here the omega qn is a slightly different from the usual definition of the quasi-normal frequency. I absorb the I into in omega. So it's omega is usually what people call I omega. And okay, let me also explain what's the quasi-normal modes in the theta. So here is a Penrose diagram of the theta, and the wedge denoted by S is a static patch, for example, and given a scalar of mass phi of mass m, the quasi-normal mode in the theta is an unshared solution, and that are regular at the origin, which is the vertical line here, and that satisfies the infalling boundary condition at the cosmological horizon, which are the diagonal lines. And for quasi-normal modes, the time-dependent part of is E2 minus omega qn times t. Again, because I absorbed I in omega. So it's like this. And t is the static patch time. And the quasi-normal mode in the theta has some very nice algebraic structure. The quasi-normal mode furnish two lowest weight representations of SO1, D. And the one with weight delta, and the other one with weight delta bar, which is d minus delta. And the mass is related to delta as delta times delta bar. And very nicely, the quasi-normal modes can be packaged into a very simple generating function, which is known as the Harry-Schroeder character. So what I mean by generating function is as follows: we can expand this chi delta q into a series of q, and the power of q gives the quasi-normal frequency, and the coefficient in front of that gives the multiplicity of that quasi-normal mode. Now we can see now let's make it more explicit. We can see the SP times SQ, or in the Lorentzian signature, the theta P times SQ. We can see the KK reduction on the sphere SQ. It gives a single tachyonic scalar in the theta P, and in the unit of okay, in terms of this delta variable, delta is between -2 and -1, and because of by definition delta bar is positive, so we okay. Next, then we expanded the character. We only care about the growing part. So the leading term is Q2 delta, and it corresponds to quasi-normal mode that grows as E2 minus delta t, because delta is negative. And the second term from the theory expansion is P minus 1 times Q2 delta plus 1. P minus 1 is the multiplicity of this quasi-normal mode, and the quasi-normal mode grows as E2 minus delta plus 1 times t, because delta plus 1 is between -1 and 0, so it's still growing. And all the subleading terms, they correspond to decaying quasi-normal mode, because the other terms start from E2 minus delta plus 2, and that's a decay. Okay, so we found all the growing quantum modes here, right? Then we plug the quantum frequency into this formula. So we have 2 times minus delta plus 1. And since delta is minus delta is between 1 and 2, the integer part gives 1, so you get a factor of 3 here. And similarly, minus delta minus 1 is between 0 and 1, so the integer part is 0. And we get just 1 here, but we have p minus 1 of such quantum modes. So in the end, what we get is p plus 2, which is exactly what we got by doing the Euclidean path integral. And this Lorentzian interpretation works for any MQ, as we proved in the paper. So to maybe it can answer Gabriel's question, like these extra zero modes can be understood as instabilities or growing quantum modes. What's still missing is the IP plus 2 parts. That's what for example Juan wants to understand by including observer. But this part is independent of that. Any questions?
Sorry, I have a very dumb question. Because can you go back to the formula where you have a direct product of SP with MQ, right?
Mhm.
But when you choose, I mean, you could have chosen the other. You could choose an MQ to be also a sphere, right? Then which one
Yeah,
you call
you can weak rotate either of them. Yeah, for example here.
But then which one? Oh, okay. So
In this case, you can also consider the theta q times SP,
yeah,
but the n depends on which sphere you weak rotate.
right. So ends up being that. Okay, yeah. So
Yeah, because if you consider if you weak rotate the other one, then you have I q plus 2 plus minus I to a different n. That n is q plus 2 instead of p plus 2.
I see.
Because the Euclidean calculation does not know which one you weak rotate. It just gives a face for the Euclidean path integral. But the physical interpretation depends on which sphere you weak rotate.
Can you do something silly and try to take the de Sitter all the way down to de Sitter? If you go to lower dimensional, you take P very small. Does that help you? That like de Sitter 2, like does the question become easier to answer where the I comes from, or does it not make a difference?
Which I you're talking about?
The I to the P plus 2.
Yeah, that's just the pure gravity. That's what Poczynski computed. That's
Oh, right. But is that
we want to interpret. We want to understand these extra i's, for example, when you have a product manifold.
right? Okay, never mind. I was just gonna ask whether.
Yeah. Okay.
Yeah.
Indeed, I have some comments when p is 2.
Okay.
It's related to some 2D. So if we consider a volume mode on the second sphere, for example, denoted, and it has a potential look, and if we go to the Einstein frame on the first sphere, it has a potential look like this. So it has a maximum at some value, and that's why this we have a tachyonic scalar in this case, because it's locally it's a inverted harmonic oscillator. And but in 2D we cannot go to the Einstein frame, and one would naively expect the theory to be described by the JT action, where phi is I use phi for the volume mode, so it looks like more like a JT action. But we know that JT path integral on sphere is divergent because the L equals 1 mode. So the L equals 1 mode. So here we have a ds square is the sphere metric, and the phi is the scalar, and the L equals 1 mode on for phi the L equals 1 mode for phi basically the moduli space of the scalar part, and it's because of that the partition function is divergent. And be careful here. Here phi is defined on in the Euclidean signature. Phi is defined on the imaginary line because you want the phi integral to impose the r equals 2 condition. It imposes the delta function. Here I just wrote down one L equals 1 mode. That's just basically sine theta. There are other two L equals 1 mode on S2. And on the other hand, we just show that the Euclidean path integral on any SP times SQ is finite. So is there a contradiction? Okay, it just means that the JT is not the full description of the 2D of the reduced theory. So we have to include a quadratic action in the JT action, a quadratic correction into the JT action. Then you get this E when you integrate over the L equals 1 mode of the scalar, you get this E2 minus C gamma square, this Gaussian factor to make it finite. And actually, if you really do the careful reduction, you'll get this quadratic action. And from the path integral point of view, it's this quadratic correction is a built-in feature. And this correction is also closely related to the wave function of the universe on S1 times SQ. In this 2016 paper, Marcena, Triaci, and Yang compute the wave function on a large circle S1 times SQ, and they found that the norm, the square of the wave function is 1 over L cubed, which comes from the Schwarzian, the one loop factor of the Schwarzian part, and some E2 minus C over L square, which is the correction beyond the JT gravity. And okay, once you have the wave function, you can compute the correlation function or other things, but you still need the measure, right, to correctly compute things. And the original proposal for the measure is just the DL in the 2016 paper. And the last year, Kohler and Jensen, they say that the correct measure is DL over L due to some zero mode residue gauge symmetry on the circle, and it turns out that's the correct measure, and we can relate to this measure if we identify L as 1 over gamma. So we have this gamma integral, and if we just replace gamma by 1 over L, we get dL over L times 1 over L cubed E2 minus the L squared. This is the psi squared part, and we automatically get the measure dL over L instead of L. And okay, and why is L, why should we identify L with 1 over gamma? And the reason is very simple. So in the global coordinate of the theta 2, right, you get the phi is the sine theta becomes gamma sinh t. And okay, in the Lorentz picture, we fix a circle near the future boundary. We can see the circle around the future boundary, and we fix the phi field at that circle. And because it's it's very late, so it grows exponentially. It's like e2 gamma, a gamma times e2 t, right? Because of this sinh t factor. And the length of the circle also grows exponentially because the metric is cosh t. And you see that from this we can see that L is phi by the fixed phi over gamma. That gives the that gives the relation, the identification of L as 1 over gamma. So yes, so it seems that the path integral can also give the correct measure for the wave function of the universe. Okay, that's almost the end. So the conclusion for talking that for gravitational path integral on SP times some other manifold, there are extra phases associated to that can be associated to the growing coordinate modes in the static patch of the CTP. And it will be interesting to study phase in other geometries, for example, bubble background. And another very interesting example would be magnetically charged black hole. And why not just the Schwarzschild theta? Because Schwarzschild theta has does not admit smooth Euclidean geometry except in the Nari limit. But if you turn on a magnetic charge, then you can have smooth geometry when the charge is the same as the mass of black hole in some units. And you can ask, well, how the phase changes? How does the phase change with the mass? And for example, when the black hole is when m is small, we might be able to treat the black hole as an observer, right? And then we can compare with the phase Huang got in his paper by including a observer. And the other question is we complexify the G Newton in some way. Do we have a deep reason for that specific complexification? Can we understand it in ADS? Because in ADS sometimes we can also get the negative modes in certain black hole background. Okay, thank you.
Okay, thank you for the very nice talk. Are there any questions from the Zoom audience out there? Okay, if not, let me. Oh, did you have a question?
You go first.
Doesn't G Newton get complexified in DSSYK in the sense of there's a Q deformation parameter.
Mm-hmm.
It's like e to the 1 over G Newton, maybe e to the -1. Is e to some power of G Newton.
Mm-hmm.
But the Q deformation parameter is either a phase or a real number,
Mm-hmm.
depending on whether you look.
But can you get
I mean,
I epsilon or minus I epsilon? That's
but I guess I don't remember exactly that makes sense, but I'm just curious if that's a context in which you can try to answer this question of
yeah,
why
that would be very.
Newton might be complexified.
What's the parameter that controls the complexification in that case?
I'm saying something very vague. I'm just saying there's a Q deformation parameter, and that Q deformation parameter is related to G Newton as I think e to the 1 over G Newton, something like that.
Mm-hmm.
And it seems like if you add a phase to G Newton, if you add an I to G Newton, you would change the Q parameter, right? So
Yeah. Q
perhaps you can understand. Perhaps in that case, the theories for different Qs on the complex plane can be understood, and then maybe I don't know.
Yeah,
I'm not sure that might help.
So well, the Q is complexified to get some phase e to minus I epsilon, something like that.
Yeah. Okay, but let me let Ludo ask this question.
So I think my question is about this program more broadly. So is the expectation that basically we're getting some, but the linearization procedure is actually giving us physical data basically because somehow the potential then turns up again at higher orders, and so it makes sense to ask what the phases and only the phases are coming from directly.
Mhm.
Yeah, is that what we're trying to do here? Because if we don't even understand the eyes from the usual leading order for the DSP, so for example, why don't those eyes have the same interpretation of just being the fact that the saddle point is unstable even at leading order? I know this is not known, but can you say some words about how this
So,
program makes sense in that context?
it's a and is there are two different sense of instability. For example, in this paper, they find this phase, right? They think that the S4 does not have any phase, and the S2 times S2 has a phase. Then then it means that the theta 4 has instability to tunnel to S2 times S2. But now it's like for example, as the theta also has a phase, then it's hard to tell what's the instability there.
Yeah, to tunnel to something else. I don't know.
Well, you know what my favorite answer to this? I think Aaron Wall has, didn't he say in one of his papers that those conformal modes come from the string theory path integral? If you just computed I mean, I think people are treating the gravity path integral too seriously, right? I mean, that's not a fundamental.
Yeah.
So didn't Aaron say something like if you try to derive the space-time effective action from the string, from integrating out the string, then the conformal mode is like a feature, not a bug. It's just what happened. So I'm just wondering whether this is a question that doesn't reside within the realm of field theory. Maybe you can't answer it within.
Yeah. Some people don't like the Euclidean path integral. They try to use the Lorentzian path integral method, like Donald Marov, or they just try to only integrate the on-shell degrees free. Then in that case, they try to avoid this and one factor problem.
Oh, so they can do the Lorentzian path integral?
Yeah, they in some sense they did the Lorentzian.
And then there's no such problem?
Yeah, it seems so.
Oh, then isn't that then a solution? I should stop
But
recording, by the way. Yeah.
yeah.
But then okay,